organizer, Professor Dong and Professor Xie, giving me the opportunity to present our work here. The title of my presentation is Building Materials Genome from Ground State Configuration to Engineered Advance. Okay, so why materials genome? As the chair mentioned that I invented this concept back in 2002, based on three knowledge we had at the time. First is CAFAT modeling, calculate phase diagram. I started in 1973. And of course, then it came from the National Science Foundation in the United States, supporting our projects. I will mention that in a minute. And then, as you know, in the United States, most of the professors have a consulting company, at least some of them. So I started a company in 2002 called Materials Genome Incorporated. So these three things made me think that material genome is the future for materials research. So let's start with CAFAT modeling. CAFAT modeling is about thermodynamic, Gibbs energy of individual phases as function of temperature, pressure, composition, and Kasai here is very important. Kasai here is for the internal degree of freedom, which means that the system can be at a non-equilibrium state. So to build this free energy, we have to have input data. We take the phase equilibrium data. We take the derivatives of free energy, like heat capacity, enthalpy, entropy, and activity. We put them together. We start with pure elements to binary, ternary, multi-component systems. And as soon as I get those functions, you can do predictions. With material design, you can do equilibrium calculations, you can do driving force, you can do physical property, chemical properties. That's the first. The second, I should add here actually the third derivatives too. So when I saw this one back in more than 20 years ago, actually started in 73, so it's 50 years now, that I realized that these are the material genome, because these properties of these phases dictate the property of interface of the materials. Okay, so if we can control them, if we can manipulate them, if we can revise them, then we can change the property of materials. And if we know them, we can do design of materials. Okay, as I mentioned, CAFAT is the modeling of the properties of free energy and the atomic mobility is for thermodynamics and kinetics. And then CAFAT has community. It has the annual conference. It has a private foundation. And it has a journal. And if you want to join our email list, if you go to this website, cafat.org, contact there, you can subscribe to the two mailing lists we have. And of course, the important thing is that you have to have tools and databases. And for community to sustain, you must have commercial products. Last week, I was in a symposium and heard Thermocac has now been 1,300 users around the world, the big companies, and there's some other commercial ones. On the other hand, if we want to sustain the community continued development in a scientific way, we must have open source tool too. So these are the 3 or 4 open source tools which we have in the community. So what's thermodynamics? Many of us, at least when I finished my college, we thought thermodynamics is only for equilibrium. But how can we talk about this non-equilibrium system, right? And turned out actually thermodynamics is not only for equilibrium. As the chair just mentioned, I think the speaker before the chair mentioned about the contribution of materials to the history of humanity. And there are 3 age divisions of prehistory and post-history of humanity. That was Stone Age, that's completed materials from the raw material. There's no change. Then we have bronze, which is copper-tin alloy, and with 12% and 20%. Maybe you can go back to why 12%, right? And you have Iron Age. And all those discoveries are empirical, purely empirical approach. Okay, so it is. I'm so happy that Professor Hongbiao Dong is here from UK, and the Industrial Revolution started in UK at 1700 to 1800. That's where it gets steam power. Steam power established the thermodynamics. Both most important, the second law. Okay. Then we have electricity. We need materials. Computerization. We need materials. So the materials, the man-made materials is the enabler for all those development. Today we have the fourth industrial revolution. It's about the digitization. Okay. Now if you think about this materials, right? The thermodynamics. So what's the digitization of thermodynamics? Okay. So let's look at the thermodynamics 150 years after the first industrial revolution. As I mentioned, that was thermodynamics established. And Gibbs, as an American scientist, he went to Europe to learn what has been created in Europe at that time. When he came back, he developed the equilibrium thermodynamics in 1973. That's 150 years ago. And then about 30 years later, he developed statistical mechanics. Okay, this is equilibrium. That's very important. Keeps that as equilibrium. And then we know that about 50 years later, we had the quantum mechanics. Then we have quantum statistical mechanics. And another 100 years about, we get a density function theory to digitize the quantum mechanics. And then what about non-equilibrium thermodynamics? As you probably know, it's Ansarger, is an American professor, got Nobel Prize, and the irreversible thermodynamics, and Prigogine also developed first for chemical reactions. And I want to emphasize that 100 years after the combined law by Gibbs, there's a CAFAD. It's a digitization of thermodynamics. Basically makes thermodynamics to be digital, that's in the 1970s, 50 years ago. And then to even further formulate it, I think it must here put this internal process due to irreversible process in thermodynamics. Now, I think it's 150 years, right? What's missing? What's the next step for us? Okay, so that's what also the chair mentioned about the entropy. Okay, and the theory of cross phenomenon, which I think is combine everything together. Okay, so as I mentioned, NSF is the key, right? Is the sponsor in the United States. So when I started at Penn State, I got a funding for education, about the inverse design and the forward simulation. And if you look at this process, we're talking about thermodynamic kinetics, crystallography, we're talking about individual phases, free energy of individual phases, mobility of individual phases, and the crystallography of individual phases. And then put the microstructure together, is different phases together. Okay? That's what I said in 2002, material genome, the building blocks are the individual phases. Okay? So then, of course, we did a lot of work. And one of the very important, I think, visionary activity at NSF back in 2003, actually started 2000, is the information technology research. So at that time, I was told by the program manager that what we do, the CAFAD modeling, was information. That was a very interesting idea to me. That means we are generating data with digitization. We are all about information. Okay, so then we developed a program which NSF supported for multi-million dollars, is to integrate the first principle to CAFAD, to phase field, to finite element. Okay, so that's in 2000, actually 2001, we got this one, 2002, we started this project, a 5-year project. So we developed this concept to put this framework in the material genome concept. You build up the property in the individual phases, okay? And then that was a company, Material Genome Incorporated. And then when I formed this company, my friends told me that I should file a protection of the name. So I filed the protection in 2004 trademark, but it took some time. 2011, when the Material Genome Initiative was started, I got the trademark. So I have a trademark here for this one. Okay, so what it means is that before 1970s, or before even before 1990s, most of the modeling started with experiment data. Okay, and then in 1990s, we started to do first principle calculations, 0 Kelvin. Then we find that we need to do the phonon calculations. Then we make our database better. However, okay, what we found is that we can do all those calculations without the ground state. And we do 0 Kelvin energy, we do the phonon calculations, some electron contribution, we get the free energy. Okay, then we say it's happy, right? It's very good. We can do all the calculations. However, we realized very quickly, that doesn't work. The DFT calculations doesn't agree with the experiment. So what's the problem? That means I have some problem there, right? That means I have the phases property for experiments, for my modeling, I have DFT calculations here. The two do not agree. They don't agree with each other. Okay, something's missing. So what's missing? So it turned out Gibbs has solved that problem. Gibbs, in addition to the statistical mechanics, in this combined law, he actually solved the statistical problem. He said a system composed of many, many other small systems. So the partition function of small systems are together equal to the total partition function of the system. Now, if you do the Helmholtz energy, then you find that the free energy of the system is a function of all other configurations, not only the ground state, right? So this goes to the Boltzmann equation too. So that means we have to go beyond the ground state configuration. Then we have the system in the experiments, they experience many more systems, just like exactly what Gibbs mentioned in 1901. He said, the system embraces every conceivable combination of configuration. That means in addition to ground state, we must have more configurations. I call them symmetry-breaking non-ground state configurations. It's basically internal degrees freedom of the phase. You can have spin, that's a magnetic. You can have polarization, which is ferroelectric. You can have atomic short range ordering, that's a high entropy alloy, for example, right? You can form compounds, get long range ordering. So that's at least we should include all of them into our free energy. Of course, if you have defects, vacancy is very important, dislocations, stacking faults, right? You can add many defects into it. So you have to put those defects into DFT calculations to do that. Okay? So what it means is that, so if you do statistics like this, right? So you say the entropy of the system equal to partition function or equal to the different configurations. Those configurations are symmetry breaking. So it's not the same symmetry as your original ground state. However, it's one big problem here is that each configuration has non-zero entropy. At finite temperature, I show the ground state we calculate entropy. That means each configuration is over entropy. So what does that mean? That means this equation is incomplete because this equation does not contain the contribution of each configuration. That means we have to modify the equation. Okay, that means we have to add entropy another part. Now we have two parts of entropy. That's from the between the configurations, and this width inside the configuration. And how do we get this one? Exactly, we talked about before. We can do DFT calculations. Okay, so that means if we get the entropy of each configuration, and then take the statistic together, then we get the complete entropy of the system. So when I give a talk to people, people say I should call this entropy. The partition function for entropy, cost-screening of entropy. So we did that one. Actually, in 2008, we did the first one. But, it took a long time for us to fully understand it. So the question is that, how does it compare to Gibbs statistical mechanics, right? This is entropy, free energy, partition function, and the probability of each configuration. So the only change we have now is that we have added the entropy of each configuration. Then this internet total energy becomes the free energy. And then the total energy of each configuration becomes the free energy of each configuration. And the probability also changes from total energy to free energy. This is very significant. Because when you change the two variables, your probability is different, right? That means the whole temperature depends different. Your free energy is different. Okay, that's very dramatic. As we know that, that's why the DFT alone for the ground state is not enough because you get the wrong free energy. That's why when we do lava calculations, we always find that we have to adjust the parameters, the energy predicted from DFT in order to fit to experiment. The reason because it misses one part of the entropy, and the free energy is incorrect. It's inaccurate. However, if each configuration is a pure quantum state means that if configuration has zero entropy, it doesn't have any unspecified degrees of freedom, then it's two identical. So it's so amazing, right? When Gibbs invented statistical mechanics, there was no quantum mechanics. So somehow he just visualized that there should be pure quantum state. And that's exactly what the quantum statistical mechanics is talking about. Quantum statistical mechanics talk about configuration of pure quantum state without any unspecified degrees of freedom. So that is not here, the series is fully complete now. The only improvement we have is that we get a more accurate free energy. Okay? So 3 ingredients for this entropy. First, configurations, quantum state and symmetry breaking long quantum state. And you get free energy from DFT for all of them. Then do the partition function with free energy. Then you get a quantitative prediction of free energy without models, without any feeding parameters. So you get a free energy of VC phase. And then even more important, you get a free energy of nanoscale. You get the barriers too. You can predict the kinetic process now. Okay. Of course, you can calculate phase equilibrium. You can predict all the properties by first, second, and third derivatives of free energy. That's basically all the properties we measure in experiments. Okay, let's talk about derivatives of free energy. That's very important because the derivatives of free energy are the properties we measure, and also it detects the stability of a system. For example, temperature and entropy should change the same direction. However, when they are non-conjugate, like a volume and a temperature, they are not a conjugate variable in the combined law. Then there can be positive and negative. That's why you can negative some expansion. And then even more important is that now we can do the free energy derivative. Then we get a lot of new quantities. Okay. For example, I was working with people since my visit in UK. Remember, I talked with a scientist from Queen's Mary University after the meeting at Birmingham. And then we're calculating the gamma 3, the linear electro-optical effect, which is sort of derivative of the free energy, which I did not do before, but turned out it can be easily calculated. And now, this is a very important concept which I have figured out in the last few years is that what do you think about the chemical potential derivative of the temperature, which turned out is solid effect. Okay, if this is electron, it's Seebeck coefficient. So that means those coefficient people thought are kinetics before actually are second derivative of the free energy. And it basically means that this equation by Ansaga and Maxwell-Stefan about the more than one independent diffusion coefficient or conductive coefficient actually are incorrect. Okay, so what it means? And I have one more slide. I think it may be 2 more couples. How many minutes do I have? I still have a few minutes. Okay, so when I was a student in Sweden, I was told that there's only one diffusivity per element, that's the mobility or tracer diffusivity, so relation to this Einstein equation. However, if you change the reference state, or change it from the chemical potential gradient to concentration gradient, you actually get a matrix now. So from one parameter, you get a vector. Okay, that's because you change the variable. Now, if you change the frame of reference for diffusion from the lattice fixed frame reference to the volume fixed frame reference, what do you find? It becomes again from one variable to become a vector. If you change the concentration, it becomes matrix now. Okay, so what it means? That means from one parameter we get a vector. This is because thermodynamics. It's a second derivative of energy. Times that error parameter give you all other diffusion matrix. They are not independent at all. But they're different values. It's because this is one value times this thermodynamic factor. And of course, thermodynamic factor is different for different element. So that's why I get the matrix. Okay? So that's very important. What does it mean? That means on some equation we have today talking about actually is inaccurate. Or actually it's I would say it's wrong actually. Okay, so what it means is that all the properties we measure, some expansion, okay, the piezoelectric coefficient, piezoelectric modulate, they are all second derivative of the free energy to the molar quantities. So if you get free energy right, the free energy, you can actually calculate all of them by the derivatives. And even more important, the diagonal terms here are positive for a stable system. But if the off-diagonal terms, they don't have to be positive. It could be negative. So if you still look a little bit, people find, we find this electrocaloric effect negative. Well, that's okay, because there's not a conjugate variables, derivatives between conjugate variables. Okay? So it's actually not surprising now if you look at this equation. And it's more important that in this set of derivatives between two potentials, for example, between the chemical potential to temperature derivation. That's a thermal transport. That's a solid effect. Okay. If this K is electron, that's some electric effect. Okay. So that means this actually Seebeck coefficient is the second derivative of energy too. Again, this because the off-diagonal terms can be either positive or negative. The question is how to predict it, right? As I mentioned, if we can calculate the free energy, we can predict it. That's exactly what we did for negative thermal expansion in our work published in the last several years. Okay, so now what it means is that we have this direct on the cross phenomenon. Okay, so it's a French landscape from the entropy theory. Direct phenomenon is between the conjugate variables, like heat conduction, okay, like the electric current or chemical diffusion. The cross phenomenon is between non-conjugate variables, like some expansion, like a solid effect, some electric, a Seebeck coefficient. Okay, temperature gradient, you can heat conduction, that's direct. Then you have the heat can drive electric current, it can drive diffusion, can drive volumetric flow. Okay, those are all cross phenomena. And if electric field can drive current, that's direct phenomenon. Then you have to drive heat, right? You can electric drive heat, that's Joule heating. Okay, electric can drive the atomic diffusion, that's called electromigration. Electric drive strain, that's called electromechanical property. Same thing for stress field too. You can drive the direct flow, stream flow, then you can do other factors. So that means those are the cross phenomena, all the mechanical, all the properties, right, we're measuring. So the theory of cross phenomena is that, okay, so the flux of a molar quantity, it's only its own chemical, own conjugated potential, like entropy is the heat, the atom is the chemical potential. But how does the heat drive diffusion, right? For example, that's because chemical potential is a function of temperature. So you get the derivative here. So that will give us the solid effect. Okay. Then the flux will also depend on them too. So this equation is what Ansari tried to solve in 1930s. But the only mistake, only the error he has is that he put all this should be potential. No, this has to be molar quantities. Okay, at least one of them has to be molar quantity. All right, so as this chair mentioned that you got this one develop a lot of tools. Okay, tools, we have 3 types of tools, which are all open source. You are free to download. If you scan this QR code, you can get a list of our codes. And if you scan this one, you get our paper and a list of the codes too. So we have 3 types of, first type of code is data generation. I mentioned DFT is important, but DFT is not sufficient, not enough. So I have to do Zentropy. Okay. And as the chairman, also this meeting means is machine learning, or AI, that we have these tools. You can download, you can install the Python superfund, you can predict material properties, and you can also even use Optimate. You have not do that. We have interface to use Optimate interface to access our data. And this one is when we are in development. Hopefully we'll be ready next year. Then we have all the data, compiled data, which you can access too. And then when you get the data, you have to process in the database, right? So we have the PACAP and SBA to process the data. And we have uncertainty quantification for all the data and the model and the model parameters and the model predictions, the uncertainty quantification. And in my first slide, I mentioned about the material design. So now we have material design, inverse design tool too. Again, you can download it for demo, and it's for high entropy refractory alloys. You can input your properties. It will give you the chemistry. Of course, it's a demo, right? So it's not fully tested yet. And we can do workshops too. Okay, so we have workshops, so we can try to do the training of our codes. Okay, so I want to close my talk by mentioning that now we have this quantitative predictive theories without the fitting parameters, except the DFT calculations. But DFT itself is not sufficient. We have to put the statistic mechanics together. So integrating quantum and statistics thermodynamics. This way we can predict the entropy So entropy will match experimental measurements by heat capacity. And then we can predict the free energy landscape. So we can calculate how difficult from this basin to that basin, or to that basin. Okay, so we can look at the reaction path through the energy landscape. So because we get the free energy accurately, so we can predict the cross-phenomenon coefficient, including the flux and all the cross-phenomena. All right, I believe that's my last slide. This is my last slide. So what's the future? Okay, so everybody think about what the future would be, right? So of course, I don't have Chris Barr to tell what the future would be, but I do have some perspectives. So I wrote a paper this year, talk about thermodynamics and its prediction and kind of modeling review, state of the art, and the perspectives. I believe it's open access if you do this QR code. And this is for the theoretical side. So what about applications? So some of you probably know Greg Olson, and I think he's the person really used the CAFAT to material design. That's why I joined his company when in 1998. And we wrote a paper together to talk about the material design and also about the future. I believe that's my last slide. I want to thank you for your attention, and I'm looking forward to interact with many of you in the future. Thank you.